Welcome to The Explainer. Today, we're going to tackle one of the most fundamental questions in machine learning. How does a computer learn to make a simple yes or no decision?
So let's start with a problem you definitely see every single day. You open up your inbox and somehow your email client has already sifted through the junk. It's made a call, this is spam, this is not. But how? How does it actually know? If you've messed around with machine learning at all, you've probably heard about models that can predict a number, like, say, the price of a house. That's linear regression. But that whole approach just completely falls apart when the answer isn't a number, but a choice, a category. And that right there is the crucial difference. Predicting a number that can be anything on a sliding scale is a totally different game than classifying something into a bucket. A linear model might tell you an email has a spam score of like 150 or negative 30. What does that even mean? It's just nonsense. We need a different tool for a different job. So what's the solution? Well, the tool we're looking for is this really powerful model called logistic regression. But here's the genius part. It doesn't just give you a hard yes or no. It gives you something way, way more useful. It gives you a probability. So here's the clever bit. Instead of just spitting out a label, logistic regression predicts the chance of that label being true. It takes in all the info about an email, crunches the numbers, and gives you back one single value. And that value is always between 0 and 1. And what you get is a number just like this, 0.932. This isn't some made-up score. It's a real probability. It's telling us there's a 93.2% chance this email is spam. And now, that is something we can actually work with. We can set a rule, like if it's over 90%, flag it. Okay, but how does it actually do that? How can a model take in all this messy input, words, who sent it, all that stuff, and guarantee that its final answer is always a clean probability between 0 and 1? The answer? Well, it lies in this really elegant little piece of math. Believe it or not, at the very heart of a logistic regression model is the same exact kind of linear equation we use for predicting numbers. It's just taking all your inputs, multiplying them by some weights the model has learned, and adding them all up to get a score. We'll just call that score Z for now. And this is where the puzzle comes in. That linear part can spit out any number imaginable, a huge positive number, a huge negative one, whatever. So how in the world do we take that wild, unbounded number and turn it into a nice, neat probability that lives between 0 and 1? We use a secret ingredient. It's called the sigmoid function. The best way to think of it is like a mathematical compressor. It's this beautiful S-shaped curve that can take any number you throw at it, no matter how big or small, and just gently squishes it down into that perfect 0 to 1 range. Okay, so look at how this actually works in practice. If you feed it a big negative number like -7, it maps it to a probability that's super close to 0. If the input is exactly 0, you land right in the middle at 0.5, a perfect 50-50 chance. And a big positive number like 7 gets you a probability that's almost 1. It handles everything perfectly. So we've got the machinery, right? But a model's no good unless it can actually learn from data. So how do we train this thing to make its probability predictions as good as they can possibly be? Well, it takes a special scoring system and some really important guardrails. We can't use the same yardstick we use for linear regression. For this, we need something called log loss. And the key idea here is amazing. Log loss doesn't just care if a prediction is wrong. It comes down hard on the model for being confidently wrong. If the model screams there's a 99% chance of rain and it's a beautiful sunny day, log loss is going to be huge. And to stop that kind of crazy overconfidence, we use another critical technique called regularization. You can think of it like putting a leash on the model. It adds a penalty anytime the model gets too complex, which is what stops it from just memorizing the training data instead of learning the real patterns. And this is why it's so important. Regularization is what makes the model actually useful out in the real world. It forces it to find the simple, general patterns instead of getting obsessed with weird little details in the specific data it trained on. This ability to generalize, that's everything in machine learning. Okay, let's put it all together. How does this whole thing work from start to finish? When you connect all these pieces, what you get is a remarkably efficient and really powerful system for making these kinds of classifications. This breaks it down perfectly. Step 1, The linear part calculates a raw score, sometimes called log odds. Don't let the name scare you, it's just the raw evidence for a yes answer. Step 2, that raw score gets fed into our magical sigmoid function to get squished. And step 3, boom, out comes your probability. It's like a simple 3-act play.
And this isn't just some elegant, abstract idea. It's incredibly practical. As the experts over at Google put it, this is an extremely efficient mechanism. It's a workhorse that powers countless real-world apps, from medical diagnosis to, yep, your spam filter. And that kind of brings us to our final thought here. Now that you've peeked behind the curtain and you get the basic idea of how a machine can calculate the odds, it opens up this huge question. What decisions, in your life or out in the world, would you actually be comfortable trusting to a calculated probability? The answer, as you can imagine, is not as simple as just yes or no.